I feel really honored to take this opportunity, or to have this opportunity to speak to everybody in the computing colloquium. Most of my interactions with the students and even the faculty tend to be in regards to the program and making sure all the students and their advisors are getting themselves straight. And now I have the opportunity to actually talk about my research. So thank you very much. So statistical tests for regularization. This is a topic that I've worked on for a really long time. And as I go through the talk, hopefully you'll be able to see the different developments that I've made with my collaborators along the way. So I'm gonna motivate the idea of regularization by looking at digital images. And then I'm going to talk about how we can view reconstructing a digital image as an inverse problem. If I could put myself in a box, you would say I'm the researcher, or one of the many researchers that study inverse methods. Inverse methods are what we call ill-posed. And I'll talk a little bit about that, but not too much in this presentation. But the result of being ill-posed is that we have to have regularization in order to solve an inverse methods problem. So with regularization, we have a lot of choices. And one of the choices we have is something called the regularization parameter. And in my talk today, I'm going to try to convince you that this is a really important aspect of regularization. And I've spent a lot of time thinking about how we could choose a good one. I've taken a statistical point of view, and through that have developed some chi-square tests or a chi-square method in order to choose the regularization parameter. As I discuss the different developments I've made, I'll show some of the applications I've done. At the end, I'll talk a little bit about learning algorithms in neural networks and how they rely on regularization, and why the regularization parameter would be important there. So let me start by showing a couple images. So here at the bottom is the actual picture that I took. This is my husband, for those of you who know him, Tom. And he and I traveled to Chicago this summer, and I thought this was a particularly beautiful picture. Got a good view of the city with the buildings and Buckingham Fountain. And then I went and I blurred it and I added noise to it. So the idea in digital imaging reconstruction is typically we're given this blurred, noisy image and we want to reconstruct the true image. What a lot of times we do when we're developing methods is we artificially blur or add noise to the image so that then we know what the right answer is, so to say, and we can test our methods and see how good that they are. So I went and used some freely available software on MATLAB to try and reconstruct the image from the blurry and the noised one. And here's a few of the outputs that I got. And I'm going to talk more about why they're reconstructed in this way, why they're wrong. This one obviously has to do with noise. And these have more to do with that choice of regularization parameter that I talked about. I would say that we don't have a really good handle on this, reconstructing the images. I've used a lot of other people's software with some of my old pictures, for example. And unfortunately, I think there's still, well, or fortunately as a researcher, there's more work to do. So now, as a mathematician, I am going to start to talk about this in terms of the mathematics of it. So what we do is we think of this image as a matrix. And that's what I mean by this notation here. So inside this matrix, well, It's not 3D, but if I'm talking about a color image, it will be. And then a lot of the work that's done is with tensors. If we just think about a grayscale image, then we're talking about a two-dimensional problem. And I'm going to focus on the grayscale image because the three-dimensional color images, we have to get a lot more into the efficiency, again, using tensors. And I'm going to focus more on the regularization parameter. So I'm just going to keep it to 2D for now. So the idea is I take my image and I represent it as a matrix. And what I do is I have an equation. And what it is I've got some, we'll call it data. This is where inverse methods, I work in the geosciences a lot too, but in imaging, we usually don't, maybe we call this as data. We have the blurred, noisy image that we assume is observed. And what we want to do is reconstruct the true quote image. Now, the formula goes like this. What we observe is that there's an operator A that acts on the true image. And that operator, at least in this digital imaging, is linear. And it typically represents the convolution with this point spread function. Now we also, in my example, I'm using noise. So the blurring comes about in this operator, and then the noise comes about in this operator. Now, as I mentioned, when it comes to inverse methods, what that typically means, if you heard that word, is that the inverse of this operator, it's not possible. And that's typically what I find it's going to be true in this application and a lot of the other ones that I work on. So this is the slide that I almost always start all of my talks with whenever I go to a conference. And pretty much anybody in the in the sessions I'm in, we always have our inverse problems set up slide, just so we can get our notation and our dimension and all that stuff right. So hopefully now you've seen how this translates into reconstructing a digital image. I'm going to do a couple more simplifications here. So what I'm going to do is I'm going to take this 2D image and I'm going to stack it in a 1D vector. So now my observed image and my true image, in addition to my noise, are of dimension, I'm calling it m tilde by 1, where I've combined it in the 2 dimensions into just 1. I'm assuming that there's grayscale. Again, this is just simplified the notation. And then here's my operator that represents the blurring. And so I guess I just can't say this enough, that we can't do A inverse. And I have to, as an inverse methods person, also give a, what's it called? Where I want to warn everybody, when you're solving problems and, no matter what's, software or system you're on, you need to be really careful, because you go to say, oh, I'm going to solve this for X. And a lot of times you'll get an answer, whatever system you're using. But unfortunately, I think they don't let you know that your answer very well, sort of the 3 issues around being ill-posedness are, first of all, a solution doesn't exist. The second one is, well, it's not true. If a solution exists, it's not going to be unique. And this is something we see a lot. And again, I'll talk about neural networks in the end. If you're, trying to find weights and biases, you could go about that a couple different ways and get different answers for the weights and the biases. The other thing is it's unstable with respect to the inputs, meaning if I change my data a little bit, which definitely will happen, then the output that I get, what I'm trying to recover, will change drastically, even if my data only changed a little bit. But when you go and you solve these problems and you do something like this, there's a pretty good chance that you'll get an answer from whatever software you're using. You just really want to be aware that it could be unstable or not unique. Okay, so given we can't do that, we can't just solve the equation. What another approach people think about is, well, let's solve an optimization problem. So the first optimization problem comes, well, we can't solve it exactly, so let's find our estimate X that minimizes the difference between what we observed and effectively the model that contains what we're trying to figure out. Now, that doesn't work either, because even though we think, we're solving this optimization problem, we're not solving it exactly. If we do this with the least squares, there is an answer. And again, this answer involves the inverse now of A transpose A. But if A is not invertible, A transpose A will not be either. So again, most of the time, we don't have this option available to us. And then the question is sometimes though, even if we did, would we want this option? I mean, do we want to perfectly match the data, right? It's a lot of times there's issues around that. Okay, so now comes regularization. So we continue thinking about an optimization problem. And in addition to trying to match the model with the data, we're going to add this second term. There's a lot of ways we can add regularization. I'm saying here, most generally, I'm going to talk about a Q norm, because the work I've done is incorporated both when Q is equal to 1 and Q is equal to 2. So how we're measuring the distance or the magnitude of whatever sitting inside here. So when I add this regularization term, some of the things I can do is I can add an initial estimate of what I think the image looks like. Now, this will be different than the quote data, and it depends on the application you're working in. The other option I have is to add an operator acting on that, and that operator could just be the identity, but it could also represent a first or second derivative. Now, why would we do that? Some people may be asking. I'll talk about it a little bit more in a second. But I wanted to also put in here some of the terminology. There's a lot of relationships with, statistics, and I do take the statistical view of things. So when we talk about ridge regression, it's going to be the same thing as taking Q equals 2. When we think about lasso, it's Q equals 1. And the main point, though, that I'm going to talk about today is this lambda and how important that is. And so if you look at these two terms, and we're trying to optimize, we're trying to minimize, right? So if we're minimizing a sum now, what's more important, right? Do we want to match the data? Or do we want to, this is also called prior knowledge, or do we also really want to rely on our regularization, which effectively is prior knowledge that we're invoking about the problem, right? So if we add this term and we add X0 along with LP, then we're really saying something about the problem. And if we believe it, then we want this lambda to be large, because this is really what's most important to us, is this information sitting here. Alternatively, if we think the data is just great, then we want to make this small, because we want to spend all of our time optimizing, or at least the majority of our time optimizing that the data matches the model. The only problem with, well, many problems, but one of the problems with choosing this lambda to be small is that we still may run into this problem where a solution doesn't exist, because we're back to just trying to minimize this. So we have to do a balance, and that's a lot of times what people think about is, how do I make this as small as possible so that I can solve the problem. I don't know if I necessarily agree with that, right? I think we need to think more, how much do I understand this information I'm adding? If I think it's really good, I want it to be large. And if I think my data is bad, I want this to be large, right? So in any case, that's my wave handing about why the regularization is important. And it will significantly change your results depending on what you choose for it. Okay, so here's a little bit more about that. So again, I'm looking at finding an image, so to say, that optimizes this. And if I take lambda large, what I'm saying is that this term, I'm trying to make it 0. So when I just have the identity operator here, I'm just giving you information about what the image is. And that doesn't usually happen in digital imaging. But what it is I believe my prior or my initial information. So here, when we think about using a derivative operator, right? So now what we're saying is the derivative of x. Well, if I say that this is 0, we're saying the derivative of x is 0, which means that x is not changing. And so that means the pixels, the elements in our matrix representing the different colors, that they're not changing. So let's think, well, I'll show some pictures next time, but that's what I'd like to leave you with. When lambda is large, we're basically saying that the pixels aren't changing. And then when lambda is small, we're fitting the data, essentially. Okay, so again, using software that a lot of people use, this was the optimal lambda. And usually you cannot figure out how they do this. They find their lambdas. Very rarely do they, like I said, there's different ways of thinking about it. Well, we want it to be small so that it doesn't really change the problem. However, what we see happening with the optimal and the large is that the images were smoothed out. I mean, this is worse than the data, right? And so what we're saying in our regularization is that the pixels aren't changing. That was the type of optimization that was used here. And so we're going to get this blurred out thing. So we got a better reconstruction with the small lambda that said, oh, we believe the data more. Right, so that's what happened in this instance. But yeah, that was really frustrating to me that I couldn't figure out how they decided this was the optimal lambda. A lot of times people call it the Lagrange multiplier, right? And then that's the whole idea of a Lagrange multiplier, again, is that you're usually iterating that to 0 because you're changing the problem. But I'm of the belief that regularization, it's not something where we want to make necessarily a small lambda, even though in this instance, it gave us a better picture. Okay. Does anybody have any thoughts or questions, I guess? I feel like, so I'm going to start getting into, this is the introduction. I'm going to start getting into this, a lot of math.
I have a question.
Yeah. Go ahead.
Yeah, how did you pick X0 for this particular problem?
This was 0.
Okay.
Well, okay. I used CAN software, and that I did know that we were in this situation with P equals 1 and X equals 0.
Okay, gotcha. I didn't see that. Sorry. Thanks.
Oh, yeah, thank you for asking. Hope you
Yeah, and you were talking about they decided a small lambda, like. So I'm trying to know who are the they.
Oh, who are the, yeah, sorry. So all this stuff I have in MATLAB. And so this is, I think the subroutine is called deconvolution reg. So it's deconvolution with regularization. It's probably the most commonly used one in MATLAB. And who are the authors? I don't remember.
Were you asking who the authors were or just who?
Yeah,
They,
because it looks like that's the state of the art, right?
oh, you wanted to know the specific authors? They refers to general practitioners in the field.
Yeah, so this one is a specific author.
Okay.
And then I'm also talking about they in a more general sense. So what I'm seeing, there's definitely people like me who really think hard about this. In fact, there's a seminar coming up, I forget what they called it, but they're like, enlightening or seeing our world clearly. I think that's how they refer, that's the title of the talk, seeing our world clearly. And it's all about how you choose this.
Is that a Boise State talk or is that a?
No, it's a Imagine, I forget what Imagine is an acronym for, but in the pandemic we've done all these virtual like seminars and groups of people. So it's international group of people who work on inverse methods. But definitely if people are interested in this, let me know and I can forward you the information so that you could watch it. It's in
They also
your
have a YouTube channel too.
Say that again?
They also have a YouTube channel.
Oh, so you can watch it afterwards. That's right. That's a good point.
That's called Imagine?
Yeah, that's the name of the inverse methods group that's
Okay.
putting a seminar together. And the next speaker the title is, did you see that?
I
Was
saw
it
the
seeing the world clearly or
every week
something?
they have,
Yeah.
and Wednesday in the morning, like 8 a.m.
Yes, at
in
8
our
a.m.
time.
here because it's in
Yeah.
Europe. Yeah.
Yes.
So the other thing, I seem to have forgotten the E. What was the E again?
That's the noise.
Oh, no, it's
And so for example, and I haven't talked that much about it, but this bad picture over here had everything to do with the bad estimate of noise. So notice I didn't title any of these with what's going on with lambda or noise. And to be honest, I'm hiding a little bit from you because it's too much information. That even in here, there's some underlying things going on with the choices for the noise and all that too. So those are two things. To be honest, I think when we know nothing, which sometimes as mathematicians we like to say, right? So, this is the noise. And you notice I have no weight on it. With my regularization, I've got sort of this weight. And we can view this as a ratio of how we're weighting the noise and the data to our prior information or regularization. So we can combine noise information in here if need be. Okay. Okay, so Bayesian inference is pretty popular these days, and Bayes' rules essentially says that the probability of X, meaning I'm trying to reconstruct X, given my data, is proportional to the probability distribution of the data. Looks like Elisa's putting up the information about decombreg. In any case, the probability of the data, distribution of the data given the parameters. Now, on the right-hand side, these are things we specify. So this requires an understanding of our data given our model, and this requires an understanding of what we're trying to reconstruct. So in a perfect world, if we know all of these things, we're done. Right? So if we understand the probability distribution of our data and the probability distribution of what we're trying to find, we can solve the problem. And so what we do is we maximize the probability that the data were observed under these conditions would be solving this problem, right? So we're maximizing the probability the data were observed. And in the end, because of the way the probability distributions are set up, we're actually minimizing these functionals that I talked about in the previous slide. But in any case, if we assume that things are Gaussian and I mentioned this a little bit before, at least in the title, then that's the L2 or the least squares norm. And one of the reasons why we like it when things are Gaussian, or we like to use the L2 norm, is because we have an exact answer. We can just write it down. When we use different operators other than L2, for example, L1, we have to get really sophisticated about our optimization algorithms. Computationally, though, with big problems, we don't form inverses, right? So computationally, we're doing something more sophisticated than that. It's just that we're, for the analysis part, I'm looking at this. And what's nice is when we look at it in this way, right? So our errors have mean 0 and covariance C epsilon, right? So that's kind of showing up in here. Now the prior, or this is the regularization, is showing up in here, right? So again, if we got rid of regularization, we wouldn't be able to solve this problem. So the covariance, or the inverse covariance, is what's regularizing the problem, right? So the inverse covariance, so if we really believe in our Gaussian prior, then this is going to be large, whatever it means for a matrix to be large, and that's going to make this whole thing invertible. And so even though we may not be finding these inverses of the matrix, that's what's going on under the hood when you're optimizing, right? And so again, something to think about, you know, when you're weighting your prior versus your data. If you don't really weight your prior, then you could be having an ill-conditioned problem. On the other hand, if you put a lot of weight on your prior, then maybe you're ignoring the data too much. Okay, so I'm thinking about things in terms of probability distributions. And when I do that, I get a result that says, if I take this answer, which is the minimum, or it's actually the maximum that the data were observed. So this X map has a formula. And if I plug that formula back into what I'm trying to minimize, what I get is that, first of all, it's a number, right? Because these are norms. I mean, I should say a scalar. It's a scalar. These are norms. I get a scalar, and it's also a random variable, right? So if I go and collect the data again, I'm going to get a different answer. So when I evaluate this objective function, it's a random number, and it follows a chi-square distribution. And what's really important in all of this, and I spend a lot of time thinking about, is this right here. What is the degrees of freedom? Right, that's what's super important. And I could spend, you know, a lot of time talking about this. What people do in practice, there's something called the discrepancy principle, is they do regularization, but when they look at the answer, the minimum, and the objective function, they don't include this part. And they say just this part has m degrees of freedom. And so what happens when you do that is you're going to get that overfitting, because you're choosing essentially a regularization parameter that's only based on this. And so it doesn't take much more to include this, and I spend a lot of time trying to convince people of that, and I could do a better job. But the idea is that because it's a random variable, we'll get a different answer, but it has an expected value, and that's the degrees of freedom. And so what we do is we say, okay, I know all of these things, right? Because I've specified this, I know that, I've specified that, I've specified that, it could be 0, the x0. I guess people on Zoom may not see me pointing to everything. And so this is something that I can calculate, but it depends on lambda. Oh, and this is, you know, I've kind of pushed my lambda into here and here to make it a little bit simpler. And that's what this is all about, is how I get my lambda from the C's up there. So then I solve this for lambda, because I'm basically saying the objective function should be m hat. Now that's another, well, it ends up being another optimization problem, because this is pretty complicated. It's a system of equations, and in any case, for most problems in 2D, I mean, it only takes like 5 iterations for me to get a lambda. What people tend to do in practice is they just plug in different lambdas and look at the picture. And so I think solving this problem is a lot more efficient than just plugging in numbers. Not only that, as a scientist, it gives you an objective conclusion, right? You're like, oh yeah, no, this is sort of the right answer, or at least it's a reasonable answer because it passes a chi-square test. Most people, when they do a chi-square test, they do it after they're done, right? This is right, so I'm thinking about this in a different way. I'm not doing chi-square test when I'm done. I'm using the chi-square test to back out what I want the inputs to be. Right? So that's a little bit different. And I've had, when I first started presenting this, people are like, oh, it's just a chi-square method. That's no big deal. We do that all the time. But no, it's solving it is the, well, that's the computational mathematician to me. That's
So you're using the chi-square test as a metric to modify the, for lack of a better word, for lambda,
Yes.
and then readjusting lambda. Based on
Actually, I don't readjust it. Well, okay. Anytime you do like a new root finding method, you have to start out with an initial guess. So there's some initial guess, yes. But the idea is that I have this equation that I want lambda to satisfy. And then because it's nonlinear, it's kind of hard to solve it. but this is the equation I want to solve for lambda. And that equation comes from a chi-square test. Okay, this was actually a while ago. But it's the idea. It's the basic idea of what I've been doing, and it's really important. Oh, okay. So this was so with my collaborator Rosie Renaud, we came up with an efficient algorithm to solve that because it's really hard. And so this is a result from that paper, and we were using. They've got an update to this now. So if you guys are interested in regularization tools, there's something more updated than this. And these are the different problems, the different noise levels. L curve, so this is generalized cross-validation, GCV. UPRE is unbiased predictive risk estimation. That's what the acronym stands for. And then there's the chi-squared method. And so in the tests that we ran, right, these are the mean and the standard deviation of the risk. And so the L curve, I'm not going to go too much in describing these methods. I think most people have probably heard of the generalized cross-validation. You know, UPRE is minimizing risk. So it was almost surprising that chi-squared did better at sort of UPRE's own game in a weird way. But also the over 500 runs, right? We had a standard deviation too, and the standard deviation even with the chi-square method. But that probably has a lot to do with the algorithm that we developed in this paper, that the standard deviation was so small. Okay, so then what I started to think a lot about, and I still think a lot about, is that we've got a covariance matrix acting on our unknowns, and we may want it to vary. You know, we may believe in the image that a certain area is more blurred than the other areas. So if a certain area is more blurred than the others, how do we add that quote prior knowledge? And we do that by having a diagonal instead of a scalar. And here I'm saying, okay, think about, I want to add some prior knowledge about the blurring in this area of the figure. And then, so I've got sigma 1s. And then in a different area of the figure, I'm going to add some prior knowledge about the blurring. And then I've got D. So I've actually got this diagonal matrix with D blocks. So the way that I looked at that was, again, going back to how this was derived, it's a chi-squared, and if you're at all familiar with chi-squared, this may feel very comfortable for you to have me write out the chi-square random variable with m degrees of freedom as k1 squared up to km tilde squared. And so then what I did is I just kind of blocked that out into multiple chi-square tests. Now we need to make sure that our M1, M2, and MD are large in order to use the chi-square test. But basically I could take these blocks and I could do chi-square tests on each block. And one of the reasons why this was important to me, while least squares has its problems, don't get me wrong, we can see here, this is a discontinuous, a one-dimensional 1D discontinuous problem, right? So the black is what I'm trying to reconstruct. If I just do least squares, you know, it's doing its best, but it's a smoothing, it's least squares. I don't know how, yeah, it's smoothing, right? So if I do, so this is one chi-square test, but if I block it up and I basically have 3 chi-square tests, then I get piecewise smooth reconstructions. So I'm still, because I'm dealing with least squares, I'm going to get this polynomial looking thing on each of the blocks. But at least I'm able to catch these discontinuities. And so when you're looking at an image, maybe let me go back to one of those images. Right, so this is a discontinuity right here because it's changing from blue to white. Right, so here, that's exactly the problem. It's not picking up this blue to white, that sharp contrast. It's just kind of smoothing it all out. And so this is one of the problems with least squares. But if you do it piecewise, it may be sort of smooth within this white, but we have the ability to jump to blue when we do the chi-square test that way. Oh, and then the other thing that's important that I was trying to make here is it's not, well, I went to that Bayesian views with least squares. When I do the chi-square test, it's for any distribution of data using the central limit theorem, right? So if you have enough data, you can invoke the central limit theorem. And so it works for normally distributed data, but it also works for other distributions. And so here's an example with the exponentially distributed data. Because that's another big complaint about least squares, which I, when looking for the regularization parameter, sort of disagree with. Okay. Here I was thinking I didn't have a whole lot to say and I've just been blabbing, and so now I'm running behind, of course. But sometimes it's the beginning stuff that's more interesting, because now I'm just going to do like a run through of, you know, more extensions of it. So nonlinear, right? Nonlinear, of course, is really important. So the objective function looks like this in a nonlinear problem. So we have f of x instead of, say, a matrix times x. And this result is using Gauss-Newton optimization, but we also have one using Leavenworth-Marquardt, if you're familiar with those methods at all. And the idea here is when we're solving a nonlinear problem, right, we iterate around some estimate. And so what we're able to show is those iterations also follow a chi-square test. It's not, you know, the end result that we could show, although maybe we could if we spent time with that, but basically at each iteration, we're finding, well, it's pretty expensive to find a regularization parameter and a nonlinear problem in each iteration. But so we would act with, depending on whichever iteration we were in that we wanted to update the regularization parameter, we would invoke the chi-square test to actually find it. And this gets messy, as you can imagine. So this is the Jacobian at that current iterate. I sort of have to bring in a new matrix, and well, it's a lot of math. The point is, we can do it for nonlinear problems in an iterative way. And so this was, we did it in a geophysics application. This is a simulated example, but I don't know if you guys have ever noticed, well, probably shouldn't advertise this too much, but on the Boise River where Highway 21 meets it, they've got some wells in there. And the idea is that you've got a well going in the subsurface of the earth. And it's almost like the brain, what people do with imaging the brain, but we're imaging the earth here. And then they're sending signals across and taking measurements, usually of the time it takes for it to travel. And the idea is to identify these structures in here. They could indicate, you know, something in the subsurface like sand or, this is just histograms just to convince you that these things follow a chi-square test. Since I'm running out of time, I'll just say that, right? So we ran a bunch of simulations and they were following a chi-square distribution. And here's our reconstruction. You know, the discrepancy principle, as much as I complain about it, I mean, it's not that different than the chi-square method. I'm not sure if you can see too much of a difference. So I think that's why people get away with using it a lot, is because it's not too off, but it's just off enough in some applications where it's not good. Oh, and then my most recent was to do total variation. Now this, this was like my baby. This took me so long to figure this out. And it's all about the degrees of freedom. And again, you don't necessarily need to understand all of this math. This was a result that I found in a paper. I don't know if you guys are familiar, how do you pronounce it, Tibrashini. He's a statistician. He's so good. I love their papers. There's two of them. There's a father and a son. And they had a paper about lasso. And I just, when I finally figured out what they were doing, it's what jumped out of my skin. I'm like, oh my gosh, that's the degrees of freedom I've been needing. And so I was able to get a degrees of freedom for the chi-squared, right? Because the whole thing is we've got a one norm here. So we don't have an exact solution. I can't just plug it in and figure out the degrees of freedom. I had to go back and really learn a lot of statistics. Well, I don't know if I learned it. I'm able to use it. Okay, so the test I did for this one, and again, this is just to kind of convince you that it works more than anything. So the idea is, here's an exact one, and here's one that's blurred. And the previous slide described what that 40 means. And then the idea is, there's not a whole lot of methods to compare this to when we get into the total variation, the way they choose their regularization parameter. Because most of those methods like GCV and the L curve and UPRE and discrepancy, but they all kind of break down because it's not least squares anymore. So what I did is I compared it sort of to the best possible. So this is knowing the right answer. This is the best possible reconstruction I can have. And with the chi-square test, I was able to get really close in many different situations. This is, again, we're kind of running out of time. I won't worry about that. Okay, so the last thing I want to say is something about, so how this applies to neural networks. So I haven't done any work, but I know everybody is, really interested in them. And so there's been a lot of work done by mathematicians to actually write down what's going on in a neural network. And so here, let's assume that we've got these pairs, feature label pairs that we're training with, right? And so we're going to stack the features into a matrix And then we're gonna try to train by matching them with these labels. And so we can write the propagation through the layers using this expression. And then at the end, we have our prediction here. So there's a lot of choices in here: activation function, number of layers, a hypothesis function. The main idea is that we need to find, when we're training, the weights and the bias. And so what happens in the learning problem is effectively we're solving an inverse problem. And so what we're trying to do is, after we've gone through the neural network, what we've predicted needs to match, or we're trying to match it with our labels. Now, right, the predicted depends on all of these weights and biases. So I could have put that this is a function of the weights and biases, and that's what we're trying to find, right? So pretty much, you know, problems with the training is that there's overfitting, you know, different, that's the other one. Yeah, this is the, I didn't mention, but you could have different weight values are going to give the same classification. That's the non-uniqueness aspect of it. And the way that we kind of fix these things is with regularization. But the issue is what kind of regularization, because we could bias the bias. And so here is a suggestion that people have made. Oh, that should be a norm. I have my things wrong. But here, basically, we're adding information that we think, or enforcing something about the weights K and the bias B. And what we're saying in regularization is that we think they should be smoothly varying, because I'm using the 2 norm or the squared, right? And so the question is, how much do we want to enforce that condition? The lambda 1 is going to decide how much we want to have smoothly varying weights, and the lambda 2 is going to depend on how much we want to have smoothly varying bias as we move throughout the layers, right? So it's kind of like the more you enforce this, the less opportunity there is for these things overfitting in different weights to happen. At the same time, what are we doing when we make those strong? I don't know. So the magnitude is really important. And again, it's something that I think that people don't talk too much about. Okay, so that's it. Where's my, there we go. So basically, you know, together with co-authors, we've got this strategy for finding the regularization parameter. It's automatic. We can develop good algorithms to make it go fast. We've done it for L2, L1, nonlinear problems, and varying regularization problems. I think it's much better than sort of heuristics. And the other thing is it doesn't, the optimization method doesn't matter, for better or worse. A lot of techniques I've seen for finding a regularization parameter, they put it inside the optimization. This like wraps around it. So that's why I use so many canned codes, is I just use their optimization and then I wrap my chi-square test around it. And then, yeah, so it'd be interesting. Well, kind of the thought of trying to figure out a chi-square test for a neural network is a little overwhelming, but it's definitely possible. Okay, that's it. Thank you.